So welcome everybody. So it's a pleasure to have Guilherme Pimentel, so he's professor Phenomenology of Pisa, and he obtained his PhD from the University of Princeton, working with advisor Mardasena. He went for a series of postdoc at the University of Cambridge, then in Amsterdam, Louvain, eventually to Pisa, where also he runs a big group thanks to a generous fat ERC grant. And well, he's a world-leading expert on the subject of these lectures and in theoretical cosmology in general, and is well known also for his pedagogical skills. So I'm very so now you're under pressure, and yeah, so please.
Okay. So my plan is to go very slow. Okay. First of all, I'm generally a slow teacher. Second, my voice is not usually like this, but I have a small daughter, so you can put two things together and guess what happens. And hopefully by next Monday you get the usual vocal range I have. So there is some syllabus. Actually, I was looking at it to make sure I understand what I have to say. Here are some these lectures have no references because this story of distributing the credit pie is a fun exercise, but it's not, I think, important for pedagogy. Actually, I really like a quote in the book of Polyakov about giving credit to different people. You may read it. You look at his book on gauge fields and strings, and right at the preface. So I'm very much sympathetic to that perspective. That being said, there are some references. These two are written for Snowmass. I participated in these two white papers. One is on the general status of the theory of inflation and connection to upcoming observations and surveys, etc., forecasts. And one is more technical, which will be the thrust of maybe I'm not sure about today, but the lectures of next week about technical computation of cosmological correlators. Then if you really love these lectures and you want the director's cut, you can't get enough of it, you want many hours of contents, then I think 9 hours of lectures on this subject for the school GGI for high energy theorists. So you can find them on YouTube. And finally, there's a very nice pedagogical set of lectures. I don't know, these people are fancy, they put it on GitHub. It's not on the archive. So if you Google if you put Daniel Bauman GitHub, then you will find that there's a link to some lecture notes that I guess is eternal work in progress. And they have many pedagogical exercises. So if you really want to learn the weeds of how to work on these subjects, I highly recommend that you download these lectures and work through their exercise. Well, I guess it goes without saying, but please interrupt me as many times as you would like to. I have no agenda, okay? My agenda is that you're excited about the topic, so I don't really have any endpoint in mind. So there are a few main messages. So I think that every good talk should start at the end, so at least you get something out of it, even if I don't get to. So what are the main messages of this sort of program? So first of all is that we have a nice calculable framework for the initial conditions of the universe called inflation. And this primordial universe is very useful to think of the primordial universe is some sort of high energy collider experiment. Good news is that potential is very high energy. Bad news, the universe just did the experiment once. So it's a low luminosity, high energy experiment. So high energy, low luminosity. So one needs to work hard to try to extract the juice out of this. In this analogy, the objects that are called cosmological correlators are the scattering amplitudes. Of this experiment. Let's see, how do I manage this? I need to get the hang of it, okay? So if you, I'm happy to take directions from this. Let's see if I start like this and slowly. Um, the detectors of the experiment are imprints on late time observables. Does it work? You can't really see this line, can you? Is it okay? Yeah. Mostly CMB, cosmic microwave background fluctuations. That's been the major and still is the leading observable from the point of view of probing this type of physics. And now there is, of course, huge effort to extract similar information from galaxy clustering data, large scale structure, clustering. And then there is a bit of a holy grail that we still very elusive, but the juice is there, it's out there. So it's 21 centimeters radiation. So this is for the students. Whenever you're working on this and people will fight you with skepticism that this is unobservable and will never be measured. Well, first of all, you should read the history of gravitational waves. And now people say, oh, everyone knew it was around the corner, which is not true, okay? And so don't worry about people's skepticism. And this is one nice reminder that in principle, there's enough pixels in nature to probe this whole scenario very far, much farther than what we have so far.
Question.
Yes.
BAO or
They're inside of large scale structure cluster. Yes. Okay. Now, this is the phenomenological thrust. Now there is a purely theoretical thrust of this whole program. So the theory behind computing these correlators oops. So the theory challenge to compute these correlators is really beautiful. There's a lot of cool connections to other branches of theoretical physics. Okay, so don't think what I'm doing is the thing connect other branches. Theoretical physics. In particular, scattering amplitudes, of course, that's why I was selling this analogy, but the machinery of scattering amplitudes is practically useful for computations of cosmological correlators and conformal field theory, because the kinematic constraints of cosmological correlators in some corners are very much connected to the kinematic constraints of conformal field theories. And I think that even here, even though conformal field theory is by now super well developed subjects, I think that we, humble cosmologists, might have something to add, which I hope next Friday I'll tell you something a bit about, because it's well, it's my pet peeve. You know, it was my first problem as a graduate student. Some other son asked me, well, wouldn't it be nice to have a formula that this, and that? And now, after lots of years, finally, I think solved it. But it uses some sophisticated mathematics. It uses twistors and Rosmanians, etc. So I hope to give a flavor of that to you next Friday. So that's it. So this is the conclusion, I guess. The reason why it's challenging is because inflation in cosmocorrelators require better understanding of QFT in current space. Okay. I mean, QFT in curved space is a subject that had a boom of activity in the 70s because of Hawking radiation and cosmological particle production, etc. But to compute these correlators, you need somewhat different machinery, more akin to the usual machinery to compute scattering amplitudes. And I think it's fair to say that over the past 20 years or so, our machinery has undergone quite a bit of development. So I'll give you a flavor of how that works. Okay, so are there any questions? So this is the main message. So I hope you're motivated, because then I'll spend the next many hours talking about this. But that's what I want you to get out of these lectures. Okay? Any questions? So this first lecture will be mostly about phenomenology. I'm definitely not a phenomenologist. I really, that's why I put this big beautiful here, because I get joy out of the mathematical physics part of this, but I do dabble. I like these subjects because it has a fighting chance of being detectable in nature, and it's a very high energy phenomenon, maybe our better shot at taking a glimpse at the Planck scale. So I think it's fair to focus a bit on the phenomenology, because ultimately physics is an experimental science, right? So we often forget in mathematical physics, but it's very important. So I will start with some phenomenology. I'll just give you an overview of what we observed and how it connects. So for this, I need both words. So here we are, us. In the US, you need to warn them that it's us, mankind, not the United States. For them, it's roughly the same thing. Here is humans, and we observe stuff in the sky. So what are the things that we observe? Let me put my artistic glare. So you observe galaxies. Galaxies. Sorry for my galaxies. They may come in different shapes, etc. And they sit on some big scaffolding of dark matter that we infer indirectly from the way galaxies move around. This cosmic web. I'm sure you've seen Illustrators, for example. If you want nice pictures, nice posters for you can just print out simulations of dark matter from Illustrators. So this is a large-scale structure of the universe that we have been observing for a long time. And now there's many surveys that are going to keep observing more galaxies, more pixels, and deeper. So there's a huge effort to see how much juice, primordial juice, you can extract out of these observations. And then at some point, the universe is too young for galaxies to have formed. There is a whole range here in which the universe is essentially only neutral hydrogen. I guess I exaggerated this. This is not up to scale. Where in principle, you could have the CMB as some sort of backlight, and you could excite hydrogen atoms, and then the hydrogen atoms would emit these 21 centimeters hyperfine transition radiation, and this would give a whole tomogram of the universe. So this is really not to scale because there is a lot of redshift range here, okay? And the universe is dark. We don't really see much in this whole range of times. We've been trying, so there's some claimed detection of the monopole of this radiation. So the claimed monopole detection.
About edges.
Yes. Yes, edges.
Edges was not shown to be wrong.
I think, well, if I understood correctly, there was competing experiment from India, but I thought that it's not sensitive enough to show that edges is really wrong. But probably most people agree that it's some systematics that they don't, but they just don't understand what the. I don't think the signal of edges disappeared. I don't think they understood the cause of what they're saying. I just put on claimed monopole detection. Or maybe not claimed. Okay, so something detected. Unclear. Then, of course, at some point, then you see the microwave background. Microwave background. When I give these lectures, I used to have a cell phone, this case. In Pisa, you can go to a shop and you can print whatever you want. So I asked them to print the CMB map. And the lady's like, "What is this?" "Oh, it's the afterglow of the Big Bang." And she didn't say a word to me after that. She just printed and to me, bye. So anyways, I'm sure you've seen this beautiful map of temperature fluctuations of the microwave background. So let's CMB, temperature order 2.7 Kelvin, and the temperature fluctuations of order 10 to the minus 5. So they're hot and cold spots to 1 part in 100,000. And that's more or less what we see when it comes to cosmological information. And then here there is the naive 0. What we today call the hot Big Bang. Okay. So this stuff looks randomly distributed, and of course, as physicists, we ask statistical questions. So we measure cosmological correlators. So what we compute, for example, here you get galaxy number counts for beams, etc., and then you need modeling to get how much matter over density there is in a certain region. Actually, I'm not a specialist on this, but roughly speaking, the type of question that you're asking is, if I see a clump of matter over here, what's the probability that I see a clump of matter over there as a function of distance? Okay, so the type of question that you ask. So you plot as a function of distance, and more formally, you use translation invariance and you plot wave number, translation rotation invariance. So you plot the absolute value of the wave number. By the way, throughout the whole lectures, whenever I remove an arrow of a momentum, I just mean this. And I will eventually start calling this energy, which you think is bad notation, but it will make sense eventually calling this thing energy. It would have been energy if it was the energy of a massless particle of the same momentum. So this will be a useful thing to, instead of saying absolute value of the momentum all the time, I'll just call it energy. Okay, so here we're essentially plotting separation in the sky, and then what we plot, for example, is the 2-point correlation function of the density contrast. Okay, and this is an interesting curve. It goes up, it goes down, it bobs. Okay, it has these little wiggles. So you take a whole cosmology course to understand this curve. It knows about the phase of radiation domination, matter domination of the universe. It knows about these baryon acoustic oscillations. Very rich curve. One sort of semi-philosophical remark about this whole subject. You can ask, what's the meaning of the average? So to do cosmology, a working assumption is that if you average things in the sky, it means that you're sampling some underlying distribution that maybe you can compute. Okay? And the idea is that different patches in the sky are just different realizations of the same underlying distribution. I think if you don't assume that, then we go home. There's not much to do in terms of explaining the beginning of the universe. Okay? So ultimately, I will relate these brackets here to expectation values in some quantum theory. So some initial conditions get transferred into these observables. But that's a working assumption. Because I gave a talk about this to atomic physicists, and they were like, oh, but why? Can't repeat the universe, right? So unfortunately, the only way to make sense of quantum cosmology is to think of different patches of the universe as different realizations of the experiment. Here, conditions. Here I'm averaging over the sky, so it's some sort of ensemble average. So there are many, so at fixed separation, there are many different patches with fixed separation, and just averaging over all patches. You just count how much over density there is in each patch at fixed separation, and you do the average.
So how big does a patch need to be in order to be?
I don't know if people test. Well, in practice, these things are described by sort of almost linear theory at very large scale. So I guess you usually take boxes there big enough that this is applicable, which I actually don't remember the number, but it's like order a few megaparsec maybe. Okay. Now for here, of course, we have nothing to measure. In the CMB, the type of question you ask is again ensemble average, but now the CMB was sort of, so what happened? The universe cools down and all of a sudden it becomes transparent, right, to photons. So they stop scattering of protons and electrons. It happens rather suddenly. I mean, of course, it's not instantaneous. So the CMB has some thickness and it is reflected in the shape of the curve. But roughly, it's a fireball. So if you had microwave eyes, the sky would look cool. It's like a fireball, right? You're surrounded by a fireball. And if you plot now the temperature fluctuations as a function of harmonic number, so you go to spherical harmonics, and you talk about angular momentum, then you see this curve that I'm sure you've seen it. It has these acoustic peaks, and then it has some damping tail. And again, the story of the peaks tells you about dark matter, the relative heights, dark energy. There's some damping tail. It sort of tells you something about this thickness. So all sorts of beautiful physics behind this curve. Okay, so clearly this is an interesting question to ask because you have some fun curve that you need to explain where it comes from. Now, the puzzle from the 80s is that the universe looks too uniform, even if you have no right to be by the time that the CMB is emitted. Never mind the fluctuations. Like if you look at different patches in the sky, look at the patch here, when the CMB was emitted, the universe was around 380,000 years old. Okay. So if you look at different patches and you shoot backward their light cones, they were not in causal contact until you hit the hot Big Bang. So how is it possible that they have roughly the same temperature? They have no right to be. So you could say it's finely tuned, but if we have a natural explanation of this, that would be very nice. Actually, this angular separation, at least when I first teach this, students think it's a huge, you need to go to very big angular scales. If you've never, do you know roughly what is the angular scale that you need to look to already run into this puzzle? If you know the answer, hold your urge to say it. What do you think? Guess. 90 degrees? No, it's less. Few degrees. Few degrees.
1,000 patches in the sky.
Yes, yes. So it's actually, yeah, it's the typical, actually, it's nice. If I had the patch of the CMB, it's the typical size of the hotspot, roughly. It's the size of the horizon. So it's just 1 or 2 degrees. It's very, so you don't need to do this. Just this is already a bit of a puzzle. So what's the resolution to this? It's essentially to give the universe more time to put these things into causal contact. So of course you cannot extend the line backwards in the hot Big Bang model because the scale factor goes like a power. The specific power depends on whether it's matter, radiation dominated, etc. 1/2, 2/3. So t equals 0 is a true singularity. But what you can do is you can put different type of scale factor and give the universe more time to make it not geodesically make the geodesics not end at 0. So that's roughly what the inflation does. Oops. I'm not mastering this blackboard. So what inflation does is some period of approximately de Sitter expansion, meaning the scale factor roughly IPhT. So now you can extend the timeline for negative times compared to this standard Big Bang picture. And then, of course, the causality puzzle is solved by just picture. No? So you keep drawing this backwards, and then you see that eventually things get into causal complex. Okay? So that's nice. But that's not the reason why we believe in inflation. So the reason we believe in inflation is that if you add quantum mechanics to inflation, you get for free a theory of structure formation. Oops. And that's a huge deal. So, people knew Zeldovich, and to explain galaxy clustering data, you needed, at the hot Big Bang, you needed inhomogeneities because you want to form structure so the universe cannot be homogeneous at time equals 0. You need some inhomogeneities so that if you put a plasma on top of it, and the plasma falls into potential wells and then clusters and eventually lead the formation to the formation of structure. So you need this surface to be bumpy. By bumpy, I mean that the gravitational potential has an interesting correlation. So at time equals 0, you need this is a 3D surface. Let's go back to wave number. You need the Newtonian potential or the local value of the curvature. I will specify later in the lectures, maybe after lunch, what exactly I mean by this. You need the local scale factor, sort of the breathing mode of the scale factor at every patch, to be almost scale invariant. If you were scale invariant, if you put k cubed here, this curve would be flat. And actually, to explain the data, it seems that you need a curve that has a little slope. This slope is highly exaggerated, just to make the point. So there's a little slope, and this has some average heights. And these are two cosmological parameters, okay? So this is called AS, and this slope is connected to something that for historical reasons we write as a number close to 1 minus 1, okay? So these are two cosmological parameters that I think are the ugly ducklings of the standard model of cosmology, because we call the standard model of cosmology lambda CDM, but the 1/3 of the show is left behind, not mentioned in the name. So I don't really want to advocate that this should be the name of the standard model, because it's not exactly something easy to pronounce, but this is more fair. So it has dark energy in the form of a cosmological constant. Dark matter gets 3 letters, for instance, it's cold dark matter, and you need very special initial conditions. Yes?
So you're blowing up the singularity into some 3D surface or by some potential?
No. So the idea is that in the hot Big Bang, there would be a singularity at time equals 0. Before you hit that singularity, the scale factor changes from T to the P and becomes exponential. Then you can keep running backwards the timeline. So there's no singularity here. There is some transition period from this inflation to the hot Big Bang. You need to heat up the universe and stop inflation. I mean, we can do it from the point of view of phenomenology, but it's hard to probe observationally. It's called reheating. You need to heat up the universe. But the observational juice of inflation is at very large scales that are not sensitive to this transition period. So yeah, so this is the old picture. So this should just be very small time. Okay? Not we don't really hit the singularity. Then here, of course, there are dragons. Okay, we have no idea how inflation started. We don't know if we just push the problem further into the past, if there's a cosmological singularity that we need to resolve. In fact, there are theorems of classical GR that tell you that this type of cosmology is past geodesically incomplete, so eventually you will hit a singularity. But somehow the gifts and the curse of inflation is that it flattens the universe, makes everything homogeneous, and somehow erases memory of the very far past. Okay, so even if there's crazy stuff happening here, it seems very difficult. There's some crazy idea of quantum gravity. In effective field theory plus gravity, we just have no chance. You can't probe this period. Okay. So how do we explain this curve here? So this talk, this series of lectures are not going to have many numbers that come from measurement, but I take pride in mentioning these numbers, and everything else is bounds, and then eventually there's just a mathematical formulae. But, at least for now, we can quote some numbers from observations. So, let's see. I will erase this. AS is actually, I gave this talk at some version of this talk at a bootstrap school, and people complained to me that of my error bar. So let me already preemptively explain. So this is a dimensionless quantity, okay? Which some component of the metric. So this is dimensionless. People are like, why do you trust this one? It's just because I copied the log of this from Planck, okay? So the log has a normal error bar. If you look at Planck, what they actually mention is log of AF, and that has a standard error bar, 0.014, etc. So this is just me taking a log of a reasonable error bar. I don't know if you care, but just NS, as I said, it's close to one number. I'm not sure that this is the most up to date. I think this is from Planck 2018 data release. Maybe they're better. Now there's this really fantastic measurement of the Atacama Cosmology Telescope that, so if Planck went all the way to L order maybe 1,000 or 1,500 from Planck, then ACT went even further, and probe really very, very high multiples. I don't remember the exact number, but factor of 2 maybe beyond this. And then you see the prediction on the CDM, like all the points with tiny error bars, and this curve going up and down, just threading to this through this point. So it's very impressive. And there might be better constraints on this.
Right, you said that the measure is slope, right?
Huh?
Slope.
Yes.
So it's from dimensional.
No, it's an exponent. So yeah, let me write the formula: zeta zeta k cubed. It's AS. You take some pivot scale to write the. Huh?
What's the scale?
I think in the CMB you probe a range of distances in the sky. You take kind of the middle range. I don't remember what. I can look up what K star is. But
150 megaparsec.
Yeah, 150 reverse megaparsecs. Okay. Yeah, but it's just that the CMB, you probe a certain range of scale, just pick some pivot. This is just to calibrate to say exactly what one means by AS. Okay, so how does inflation explain these numbers? So the idea is that this universe is expanding, and because it's expanding, there's cosmological particle production. It's exact same physics of Hawking radiation or Schwinger effects, etc. Exact same physics. So you have just vacuum fluctuations that usually disappear. They pop from empty space and they annihilate immediately. Here, there is often the chance that these are pair produced and they get stretched by the expansion of the universe and they go on the mass shell, essentially. Okay, and this is efficient enough that it gives rise to this type of curve. So what happens is that you have this sort of EPR pair, and then the particles go on shell. And the kinematics of the Sitter space is such that this almost scale invariance is very easy to wire in. So you have these pairs being produced at all times. And with this picture, I want to convey a little message that things that are imprinted at large scales, they were sourced earlier during inflation. Okay? So the larger distances you probe in the sky, the further into the past that you're probing inflation. So there is some sense in which you can trade time evolution during inflation by correlating different distances in the sky. By the way, if you look at this curve in the CMB, this flatness here, at very large scales, there's not even time for the plasma to undergo any interesting dynamics. So this part of the curve modulus some small projection effect is essentially this curve here. So you see from the data of the flatness of the initial conditions. But then with these initial conditions, if you put this as initial conditions for gravity with some plasma and some Weiss's equations for fluids, then you see these acoustic peaks, etc. And it fits the observations for these two numbers. So there are some natural questions that I guess one should ask right after. So this picture is very beautiful. So standard lambda CDM is just this part of the board where you just postulate that at time equals 0 you have this k cubed zeta zeta. You just postulate this, okay? And the people knew that you needed this curve to explain some observations even before inflation was proposed. Now, inflation explains the curve. It gives a mechanism for producing these density perturbations at arbitrarily large scales. This scale invariance is a consequence of some sort of time translation symmetry of inflation. Now, one could say that this is also a prediction of inflation in the following sense. That inflation, of course, must stop. Otherwise, you need to glue. The Sitter is geodesically complete. In principle, you can keep expanding forever. But inflation needs to stop so that you can patch it up into the standard hot Big Bang universe. So this eventually needs to start slowing down. So strictly speaking, this is approximate, and the Hubble scale should very slowly reduce over time. And the typical fluctuation, if you take a canonically quantized field that is very light, the typical fluctuation, we're going to see that later, is controlled just by dimensional analysis by the only scale of the problem if it has no mass, which is Hubble. Okay, this parameter during inflation. So you see, if the Hubble parameter is reducing because the universe needs to eventually get out of this accelerated phase. If h is reducing, then it means that the fluctuations need to become weaker. But they're becoming weaker when h is smaller, but when h is smaller is towards the end, and this is when the fluctuations that are correlated over short distances are formed. So when you go to high k, you're probing short distances, and then the short distances are sensitive to a smaller value of Hubble. So if you wish, this exponent being small is some sort of prediction. It's really a prediction because this was only measured after the original papers on inflationary perturbation theory. It's a prediction of this, that this type of framework makes sense. Now, so that's the historical perspective. If you go and treat inflation from a more formal group theoretic, if you wish, perspective, all that this number tells you is that this was a very light particle. So one way to think about this number is that this number is a measurement of the mass of this. Gives you some spectroscopic data about this particle. So roughly, ns minus 1 is connected to the mass of the particle in Hubble units. So in the sitter, there is a new story about representation theory. In flat space, particles are massive or massless. Our inability of probing massive and massless particles have to do with the scale of our experiment. Our experiment has a typical energy scale, and then things are heavy or light compared to the collider, but it's a human-made scale. The sitter has an intrinsic scale, which is Hubble. So there is an intrinsic sense in which particles are heavy or light, and it changes the representation theory. If you do representation theory of the de Sitter group, is quite different from representation theory of the Poincaré group. There's all sorts of bizarre things that happen. Also, happy to tell you.
In this context, the particles are like standard model particles, or they're excitations of this?
No, we don't know what this particle is, so we call it the inflaton because we have no idea what it is. Now you can ask, what could it be? And scalar that is a natural candidate is the Higgs, but I think in detail the picture requires some extra bells and whistles, so it's not very minimal to even assume that it's the Higgs.
But then the statement about the Stringer effect that you're talking about is it with the inflaton field specifically?
That's right, yes. But any particle, including standard model particles, will undergo Stringer production here. The problem is that even if they're light but fermionic, they are very badly pair produced. I don't know, some poly blocking. You see from representation theory that you get essentially here because it's light and bosonic, you get some amplification of particle production. And you see there's a little tension because we're saying inflation washes everything out. And we're saying there's particle production, something survives. So what gives? So there's some delicate balance between the particles being produced and redshift from the expansion of the universe. And for very light scalars, these just so happen to precisely balance. If you take, for example, even massless fermions, redshift wins and nothing survives to late times. Okay. Another example, if you take spin 1 particles, photons, also redshift wins, which is, well, we can debate if it's a puzzle or not. There is some evidence that there might be magnetic fields in long enough scales that, well, I think it's not entirely clear, but it could be that they have a primordial origin. And we don't, to explain it from inflation is a challenge, precisely because of this. And some, well, but funny enough, for massless scalars or very light scalars, it works. And for the graviton, it also works. So spin 1 in 4 dimensions is a particular beast because of conformal symmetry. But then you go to massless spin 2 particles, the same mechanism works. And that's a main prediction of inflation. You give me good leeway. So these are the growing pains of the universe. So the universe is stretching, expanding, and then it should produce gravitational waves, okay? Correlated over very long distances. These are very weak, very hard to detect. So the main probe for detecting them is that they create tidal waves and they change the polarization pattern of the CMB. These things are called B modes. So the CMB light, because of scattering with electrons, it's polarized, so it has some net linear polarization. And if you look at the CMB map, the idea is that if you found a hot spot, you should see some swirling pattern of the polarization around every hot spot. So this is called B mode polarization. Okay. So if you detect B mode polarization, there are two possibilities. It's either primordial gravitational waves or it's dust, contamination from late time. So
About the spin one where the redshift wins. If the spin one had a little bit of a mass, not a phone, or something else.
the redshift keeps with. So the best chance is to make the mass as small as possible.
Yeah,
Zero?
but
So
there's an extra scalar degree of freedom in it. Does it?
If you think of Stuckelberging, do you think that the mass?
What would happen?
I don't think I don't think that I think that all degrees of freedom will get redshifted. We can try to understand from the Lagrangian why that's happening. Maybe it's something about. I mean,
Because when mass goes to zero, one free goes around, then there's a shifting.
I'm trying to understand now from. Yeah, I'm a bit puzzled, but yeah, I think I need to think about it a bit more. But the usual statement is that the Sitter metric is conformally flat, right? So I'll explain that in a bit, but just to make the point. So this is the Minkowski metric eta, bad notation, so G flat. And if you write this is the action. So you see that the root G in 4 dimensions precisely cancels the inverse matrix for spin 1. Right? So then the fact that it's in curved space is irrelevant for photons. That's why they're redshifted. Now that being said, if you add m squared, it does look like a mu pi. This phi does look like a massless scalar field in the Sitter, right? They seem to have the same type of Lagrangian. So I don't know. I need to think about it. Yeah, I'm not sure. I need to think about it if the equation of motion of this pi is identical to the equation of motion of a massless scalar in ds. But that's the by the way. So of course, photons in. This is a 4-dimensional statement. If you change, the universe was not 4-dimensional, it would be no problem. Produce photons in the Sitter space. But okay. About gravitons. So of course we have not detected them, but the predictions will be very similar. Yes.
What's the difference between the scalar particles and the temperature fluctuation?
So the rough, this is very rough. At large scales, it's order 1 number, delta t over t. Now, what is zeta? Zeta is the local scale factor. So if you take a time slice, that hot Big Bang, so it has some scale factor A of t. And the idea is that if you take a little patch, depending on the value of zeta, so zeta 1, zeta 2, here the scale factor, so all the matter that is inside of this patch feels a scale factor that is like A of t times 1 plus zeta 1. So it's a small perturbation. So different patches, they experience slightly different scale factors that is modulated by this zeta. So this zeta is a component of the metric, and through Einstein's equations, it's related to the fluctuation of the inflaton. Okay, then delta phi, the fluctuation of the inflaton, then through Einstein equation or some Higgs mechanism, it's absorbed into some longitudinal part of the metric, and then at large scale, so this is at very large scales, when for this part of the plot is essentially some number that is controlled by the matter, by the equation of state of the universe and the temperature contrast. Okay. In more detail, then you need to understand how these peaks come from. But that's the rough. So that's one reason to understand why the temperature contrast is of order 10 to the minus 5. Remember I said that this is order 10 to the minus 5. So then zeta will be of order 10 to the minus 10. And that AS AS is minus 10. Okay. So I've been going for 1 hour, right? I think I'm happy to continue, but maybe for my voice, it's better if I take. Can we take 10 minutes and then I continue?
As you wish, yes. Maybe you can take some question right now if there are.
Sure.
Somebody has questions. No. So.
Yeah, we'll take 10 minutes and then we
Yeah.
continue.
Five. Okay.
You had a kid, no? But long so going to the daycare already.
Yes.
So getting sick all the time already.
Yes. Like this, just You
Okay.
can go.
I see. Okay, so we would like to understand inflation, have some idea of what this field responsible for the curvature perturbations, where it comes from. Okay, so natural question is to ask what is this delta phi? We call it inflaton, and you have two puzzles to explain. One is to explain where these fluctuations come from, how to embed it in some bigger theory, and also to have some theory of the background, H of t. Okay? Now, I would say that this is really all we know from observations is that you need to explain zeta, zeta. Well, you need the universe to be homogeneous, right? So homogeneity plus uh, so how do you explain this? Now, historically, the simplest model of inflation does this for you. But I wanted to frame the discussion this way to remove ourselves from the historical straitjackets of model building. Right? Because it might be that this is the way nature operates, it's very minimal, it explains the data, but one should be open-minded to the extent that this is all we really know. So there might be other possibilities out there. So the typical way to UV complete this is just to in other words, to embed this in a theory that explains where the fluctuations come from and gives rise to this background evolution, is to put this inside of a bigger field. So you have a field phi. The field phi acquires some classical time evolution, and it has some fluctuation. Okay, and then you say that this classical time evolution comes from the fact that the field has some potential. There's some v of phi. We'll explain what this potential is to look like, and so then what you see, this phi bar comes just from classical evolution. And this delta phi really comes from the fact that the classical evolution is not exactly the same everywhere. So different points, all points undergo the same classical evolution, but some are a little bit fast forwarded and others are a little bit delayed. Okay, so actually it's useful to think of the fluctuation of this field as a clock. So all that this delta phi is doing is every point in space undergoes the same history, just rolling down this hill. The rolling down the hill is because the potential energy of the field source is effectively a cosmological constant. So that's what makes the universe expand. Okay. And the fluctuations, all they do is they delay or advance a bit this history. So the universe inflates a little bit more, a little bit less, but they all inflate the same way. So you get this bumpiness just because this patch, the universe expanded a little bit more, this patch expanded a little bit less, but they all undergo the same history. Okay? That's why I call this clock. So this has many names. We call it single field slow roll inflation. In this particle physics analogy, it's like some Higgs-like UV completion. In the sense that this delta phi is this field is some sort of Goldstone of time translation symmetry. So you see that everywhere you undergo the same history, and this delta phi just changes a bit the history. So you should think of it as a Goldstone boson. and it has its own action. It's called the EFT of inflation. Maybe I'll say a little bit about it after lunch. And it's very much similar. It has similar structure to the nonlinear sigma model. Okay, it's slightly more complicated because of the pattern of symmetry breaking, etc. But it looks like a nonlinear sigma model. In particular, it has some strong coupling scale. You need to decide how to UV complete it, etc. So that's the simplest way to UV complete it. But it is a way of UV completing it. So one should not. Often you'll find it's always useful to have models to have an idea of what's going on, but we don't know that this is how nature operates. So, for example, you have string theory colleagues in this institute, right? So a lot of the debate on what's called the swampland is whether in string theory you can engineer this potential, okay? Because this potential, as we'll see, has all sorts of interesting properties. It's rather flat. In many models of inflation, this field phi has to roll quite a bit range in field space, like almost Planckian field range. So as an effective field theorist, you might be a bit worried about this. But we might be barking at the wrong tree also, because we don't know that this is how nature operates. So even if we say, no, from the UV it's impossible to do this, then all it should be telling us that we should think of other mechanisms for inflation, because we don't really know that this is done. Then in this framework, you can add additional degrees of freedom, like they're spectators. They don't take part in the background evolution, but they undergo particle production. So you can add, for example, spectators. And then this starts to become a little bit like the electroweak theory, in the sense that it's a weakly coupled UV completion of some theory of longitudinal modes of W bosons, etc. So it's very weakly coupled theory, calculable, everything is fine. But we know the nature, for example, if you think of this delta phi as some pion of some nonlinear sigma model, we know that nature has other ways. So another way, and this is the road less explored. So I'm inviting you. I try to dabble a little bit on this, but I think that there's a lot of fun stuff to do here that has not been done, which is the QCD compositeness way. You learn that you should not split words in English, right? So, but I'm Brazilian, so we learn to split words in school. Do this. And here the question is what? What's the benchmark model? Is there some model that gives rise to this expansion of the universe, and then has this inflaton, it has maybe other smoking guns of compositeness, other states, etc. So I would just put this as couple UV completion. I think this is a very interesting direction to work on, because it's not very well explored. And as I'll advocate later in a few minutes, the searches for new physics, they are driven by what you're looking for. At least up to today, it's not that we measure the correlation functions of the data. We, at least beyond 2 points, if we're going to probe higher point correlation functions of the data, we need to know what we're looking for. It's a bit like gravitational wave searches. We build some templates from theory, and then we contrast the templates with the data. We don't measure the correlation function of the data and see what is the physics responsive for it. So it could be that there are interesting scenarios that we just haven't built the templates, so we just haven't looked for it. And if you look today, with data that exists from Planck, etc. Yeah.
Compositeness, you mean that the inflaton itself is a composite particle?
Well, yes, that would be interesting. I don't have an example of a model where that happens. So, I mean, simple things you could imagine. So, the things I did are very simple in this direction. So, you could imagine coupling the inflaton weakly to some sector that has large anomalous dimensions, like some CFT or some Randall-Sundrum model, something like that. But it would be nice if I think it would be more motivated to have everything be composite. So the inflaton and all sorts of other stuff that comes around for the right comes from some strongly coupled theory.
But does this somehow exclude composite Higgs models that exist for like particle phenomenology?
Uh, why do you say that it excludes?
I'm asking
It could because this we know much less about this than the Higgs, so you could recycle that for this type of scenario. Now there is one motivation to. I mean, there's no hierarchy problem here, strictly speaking, but this field is very light. So remember that to explain an S minus one.
In the composite model, you mean there's no hierarchy problem?
No, I mean in inflation, there's no. Well, because an S minus one is connected to M over H. So in principle, there needs to be a very light scalar in the spectrum. However, there are no Yukawas. I mean, in principle, there's no. You could imagine some UV theory in which the inflaton couples to everything else in a shift symmetric way, and there's some potential that has the desired properties in the UV, and the shift symmetry of its coupling to everything else protects it from quantum corrections. Okay, so maybe then the question is, can you engineer this very flat potential? And for example, string theorists would say no. It's difficult. So it is. There is some, I wouldn't call it the hierarchy problem, but there is a little challenge in explaining where this very light scalar field comes from. Maybe it's not as dramatic as the hierarchy problem. So maybe some of these ideas could help. There's also, I mean, because we have only detected this field, it's not obvious that maybe right above or their Hubble, there's all sorts of other states, and then somehow everything is fine. But we haven't seen evidence yet. In this framework that is rather minimal, appealing because it's minimal, I would say there is a challenge of explaining why the inflaton fluctuations are so light. There's some sort of hierarchy problem. Okay. So this is an invitation. Okay, I have had one student that is finishing now this year. That spent most of his PhD thinking about this, but we're doing some very simple things. Just take the inflaton weakly coupled to a strongly coupled sector, and you see that the types of correlation functions that you get are not exactly the same as you would get from weakly coupled models. So, but we're just beginning to explore. I think 99.9% of the literature on inflation is here. Although here there might be opportunities. Yes.
For large extra dimension, could you engineer such a thing, or?
Well, I mean, it depends on what the large extra dimension is doing. Of course, if you couple the inflaton to some CFT with very large anomalous dimension, in some sense you are adding some, if you think in ADS CFT, if it's very strongly coupled, you are adding a large extra dimension. That's what Randall-Sundrum is doing, right? So if you want the theory to be strongly coupled and gapped, then you add the chunk of ADS, a bit of large extra dimension. But we played very simple games. So for example, one thing you can do is you can couple the you can couple the inflaton. So with this shift symmetry, protects whatever dynamics gives rise to the background, to some operator, and then this operator can have an interesting two-point function. So one way of thinking about it is that if you have, let me now take this picture of inflation that I've been writing on the board and tilt like this. So there's a little brain here, which is like inflation. So for example, if you want to compute a 4-point function, you'd have 4 of these phi's here. I'm jumping a bit ahead, but and this correlation function of O would come from some strongly coupled sector, and the magic of RS and holography, things like that, is that you can just think of some weakly coupled particle that probes the extra dimension, right? So that's the. And then the question is, what sort of bulk do you add? And there's something interesting that happens here, because again, there's a question of the gap of the steering Hubble units. So you can, so this, if this O comes from, yeah, this is very apedagogical because I'm jumping far ahead, but okay, just for fun, okay? You can, if it sounds like Greek, forget it. We'll go back in a second. Comes from theory. QCD like theory M gap. Then zero Hubble. So if the gap is up here, then this bulk is very small, and then it's almost the same as just exchanging a heavy particle and the original inflation. So this is not super interesting. Here, it's like coupling it to the CFT, so you don't really need to do this fancy extra dimension. You can use conformal symmetry to just compute this correlation function, because you know what the two-point function of O is. But you can imagine that if the mass gap is down here, you can add a chunk of ADS, some infinite ADS throats, put some massive particle here, and it's this sort of diagram that was computed. Now here it's more interesting, because what happens is that the throat is not infinitely long, but you need to engineer a mass gap, and the way you engineer the mass gap is not by putting an end of space-time. Space-time develops a horizon. So actually, when discussing Raman Sundram, he was saying that one of the RS brains get fried by the de Sitter temperature. So one of the brains here that usually caps the mass gap fluctuates so much, it gets sort of fried, and you develop a horizon. And behind the horizon, there's a cosmology. So it's kind of neat, the scenario. I mean, the Penrose diagram looks something like this. So this is this inflation. And then there's a horizon here, and there's some open FRW cosmology behind the horizon. The horizon is here. So this is one of the things you can, but this is very primitive. You know, it would be fun to have an actual model where everything is under control and the inflaton itself is a. And we played games at the level of perturbations. We haven't tried to engineer the background solution, because you can just separate what's responsible for the dynamics of the background and what's responsible for the dynamics of the fluctuations. Anyway, okay. Back to our usual schedule. But I make this point for two reasons. One, to emphasize that this is not inflation. Historically, this is how inflation was developed, but from observations, we don't know that this is inflation. So one should not be overly attached to this picture, despite the fact that almost every inflation seminar starts with this picture. It's always good to have models, to have expectations of what should happen, but we don't know that this is the way nature operates. And this is a bit of an invitation to think of alternatives. It's not alternatives to inflation, just different mechanisms for inflation itself. Okay. So how do we learn about microphysics? So if we want to learn about things at short distance, we just put them under the microscope, right? And if we run out of microscopes, we just mesh them. So scattering. In scattering is related to a higher point. This scattering is a much cooler name. They're just mashing things into each other. The cosmologists were not very good with PR here. It's called the primordial non-Gaussianity. So, but it's the same thing. Okay. So that's this is the object that is the probe of interactions. Delta. Okay. So, for example, for the rest of these lectures, we stop here. So we don't discuss this anymore. Maybe I mentioned something about bounds, etc. But when it comes to actual computations, we just want to go from inflation to the end of inflation. So we'll just do half of the job. The second half requires codes and etc. So now time goes up. And what we discussed so far is the two-point correlation function of this inflaton field. And all we really know is that the mass of this delta phi is very small in Hubble units. Okay? So inflation, or the seeker, has an intrinsic scale h, and that's all we know. By the way, maybe I can say one more thing. One could ask, I can say one more thing. Maybe one more thing about phenomenology. The scales. Let's see. So there's M Planck. There's some UV cutoff for inflation itself. Then there is, in this analogy, if you write the kinetic term for the inflaton perturbation, some sort of pi Lagrangian form. So this is a very light Goldstone boson. There is the Goldstone decay constant F, I guess squared, right? And there's Hubble. And then there are all sorts of unknown scales. Actually, we have too many unknowns and too few observables, which is the problem, which is why so much is done in model building inflation. So we have only measured two numbers. So they're the things that we have measured. I'm just trying to show what the measurements tell us about these scales. So this lambda UV is the scale at which the pi Lagrangian is breaking down and requires some UV completion. Okay, and, or the whole scalar sector is breaking down. This is strong. strong coupling. For a scalar. Here. This is, of course, strong coupling for gravitational. So we measure two things, which are AS and its dimension, as I said. So AS is really controlled by the ratio between these two scales. Okay. The ratio. So we don't know what Hubble is during inflation for that reason, because we know this number, but all we know is we measure, if you wish, in Hubble units, the pion decay constant for this Goldstone. In slow roll inflation, it's related to phi dots, the speed with which this classical solution or the inflaton is rolling down the hill. Okay. So yeah, let's keep that in mind. So if we have slow roll inflation here, and as the inflaton rolls down the hill, it has some typical speed, pi bar dots, and I guess this is of the order, sure, maybe square root of 5 dots. This.
The initial condition of phi dot, or because phi dot is kind of purpose. There's also phi dot, I guess.
But in slow roll inflation, somehow is the other time derivatives are even smaller. So let me just explain why it's controlled by phi dots. So if you have fluctuations order one, then the pions are melting down instantaneously, so it doesn't make sense to talk about pion Lagrangian. Here, if you had fluctuations of the order of the average speed of the kinetic field, then it doesn't make sense to break the evolution of the scalar field into VAV plus fluctuation, right? Because in every Hubble time, you fluctuate roughly the same amount of displacement that the field had. That's why it's controlled by phi dots. This is AS. Now, the problem is that NS is controlled by other scales, and then it's phi double dots, etc., that you are asking me, they appear. So NS is controlled by a ratio of Hubble to some other scales, which is how slowly Hubble is changing over time. But it's not clean. It's not that it's pinned to a single scale, and that's a bit of a problem. Now there are things that are targeted that we would like to measure. I'll mostly focus on primordial non-Gaussianity, but there are other things. So first of all, there's of course primordial perturbations of the graviton, tensor modes. And this would measure Hubble in Planck units. Okay, so the strong coupling scale is the Planck scale. For tensors, now, then there is a primordial non-Gaussianity, which is like higher point functions. And roughly speaking, they tell us something about the UV completion of the model. So, but they relate all sorts of different scales on this range. So it's rather rich, but you need to have some specific model in mind to understand what scales you're learning to correlate. So this in a figure is kind of the problem with inflation. There are only a couple of observables, and there are quite a few scales that appear in the model, in the typical model building. So we need more detections of stuff to understand. For the standard model, we have lots of measurements, and we can relate to almost all the scales of the standard model. Then we look for perhaps hints of new physics. Here we have only essentially two measurements, so they don't really tell us a whole lot. Tensors are interesting because this is rather robust in the sense that it's difficult to fiddle with the fact that the tensor modes probe the ratio of the Hubble scale to the Planck scale. It is possible, but it requires some modeling. And therefore, if we measure tensors, then we would know what Hubble is.
I think what is the bottom?
NS?
Yes.
I just meant that there are other scales here that are controlled by H dot and H double dot for NS. And of course, then this depends on what is the actual physics that gives rise to NS. But in slow roll inflation, it's controlled by two slow roll parameters, so you can't really pin.
So it's not very west because H dot.
No, I think that there are factors of M Planck, etc. So that they're not. I don't think they're the same scale. I need
Anyway, F is phi dot over mass Planck.
Yes.
Yeah. The square root.
Well, here it might be.
Divided by.
Let's see.
Because it's the square root of epsilon times h.
Yeah, it's usually.
And epsilon is phi dot squared over h squared.
Right, so usually the kinetic term of the inphoton is like this, right? And then epsilon, as you say, is pi bar dot squared over. No, this doesn't make sense. Dimension. Sorry, I'm just confused. Pi bar dot squared is h dot, right? This
Yes.
yeah. M squared. So what appears here is m Planck squared epsilon, which is m Planck squared h dot over h squared. So I guess this should be h like this. Agree with this?
If you take the square, so if you take the square, I think you have to go down the square.
Yes. Bar dot over h. No, but this doesn't make sense in terms of units, so why am I doing wrong here?
Why?
Because phi has dimension 1, and there. So this is dimension 1, 2, 3, 4. This is dimension 4.
Yeah.
So start again. Right. So no, I think that's right. So the problem is with pi is that you need to convert from zeta to pi, which has a factor of h, right? This was m Planck squared. Sorry. Epsilon squared h squared, but the zeta is minus h pi. Is that true? Zeta is minus h pi.
Yes.
Then d pi squared then f is phi bar dot. This I still don't. Anyway, maybe I should look this up after lunch and tell you what that is. I always get confused by this. But The point is that they're in slow roll. There's always phi dot appearing here and here, but I think they're multiplied by different things. So that's why I put them down here. Let me look this up. Fix it later. Okay. So let's go back to this picture. And so here is the mass of one of these scales. So the simplest thing you can look for is the 3-point function of scalar fluctuations, but you can ask all sorts of different questions by more than one Gaussianity. So this is the object that has been most studied by far in the literature, but there are equally interesting objects. There's this one, the 4-point function of this curvature perturbation. And when 2014 BICEP claimed to detect gravitational perturbations, there was excitement about graviton correlators. And so, for example, you could imagine during this, and because of light birds, there's even some interest now in like this type of objects, because we don't know how non-Gaussian, I mean, strictly speaking, we don't know how non-Gaussian the gravitational sector is. Probably very Gaussian, but okay. It's actually the gravitational sector is very difficult to fiddle with, and it's a bit of a challenge to crank up this graviton 3-point function. The only examples I know, they require some so you have some gauge field that you do something funny to it, you trigger some tachyonic instability, it linearly mixes with the graviton, and it enhances the 3-point function. But it's rather delicate because it triggers tachyonic instability to stop it, so that you don't back react. So this is a challenge actually. This is rather robust, rather robustly very small, robustly almost undetectable. To make it large is quite interesting. This one has some interesting story connected to representation theory, that the type of object that we usually search for here is forbidden here. I'll explain that a bit in a second. So, what kind of physics can you infer from measuring a 3-point function? So there are a few possibilities. Possibility number one is that the blob just tells you about some cubic self-interaction. Okay? Just learn about self-interactions of the curvature perturbation. Okay? I said it's the local scale factor, but it controls the local curvature of the universe. Okay? Because you change the scale factor. So we call this curvature perturbation because the linearized Ricci scalar, when you add this term to the metric, it's proportional to the Laplacian of zeta. So it's also called the curvature perturbation. So you can learn about self-interactions of zeta if you have a contact interaction. So from here, without doing any calculation, you can tell what the signal is going to look like. Because remember, in inflation, space tells you time. Right? So even though you have a static snapshot, the cave of Plato, right? Just like in holography. You see the cave, there's some static pattern, and from the imprints at a given distance, you infer things that happen further in the past. Okay. This is a big theme in holography because de Sitter is the close cousin of anti-de Sitter. So many of the intuitive pictures that we get in holography are also applicable here. In holography, we relate distance scales to energy scales or G flows. Here we relate separations in the reheating surface in the hot Big Bang to earlier or later times. So if there's a self-interaction, there's a single time in which the fun happens, no? In which the particle self-interacts. If there's a single time, it picks a single scale. There's a single separation for every time in which the signal peaks. So it will peak when you take an equilateral triangle. If you have a triangle of different shape, each side of the triangle has a preference for a different time for the fluctuation to be sourced. Of course, quantum mechanics, so it's not a sharp peak. There is support everywhere because you path integrate, etc. Quantum fluctuations, but the overwhelming signal is near the equilateral triangle. So for this reason, this is called equilateral non-Gaussianity. So this is me giving praise to cosmologists labeling of certain processes. This will soon become a disaster, but this makes a lot of sense. It's called equilateral non-Gaussianity because it peaks near the equilateral limit. Then, what sort of other possibility can you have here? You can probe messengers. You can have a messenger. The messenger can be a single particle state, can be in a weakly coupled theory, can be the two-point function of some composite sector. It can be a loop. It can be an elephant. We don't know how to compute in that case, but it can be whatever messenger you want that is produced by quantum fluctuations. And you can probe messengers. And here you open up a whole menu of possibilities, right? Because it depends on the details of the messenger. Now, there is a tension because messengers are happy to take a message from A to B, but the universe is expanding, so there's redshift. So the messengers, if they're heavy, they quickly fade away. So there's, again, this tension between how heavy the messenger is and how many Hubble volumes you can traverse before it is very small amplitude to communicate or to decay into curvature perturbations. So this is interesting as long as the mass of the messenger is near or below the Hubble scale. And it's most effective when the messenger is massless. Of course, when the messenger is massless, you can propagate arbitrarily long distances and not decay. So the main second probe of non-Gaussianity is the massless messenger limit, okay? Because you can correlate modes. So now you can create huge hierarchy between these modes in the triangle. In particular, this messenger is very light. You can have a triangle, so K1, K2, K3. So if you're in momentum space, there is drawing this picture, there is a huge cognitive dissonance, so I need you to accept this. So this is called the long mode, and these are the short modes, even though, as you see, these are the long sides of the triangle, this is the small side, because these are wave numbers. And so this is the long wavelength mode, so it was sourced early during inflation, it has very long wavelength by the time we measure correlations. Well, these ones have very short and nearby wavelength, so they were sourced towards the end. Then you need a hierarchy of times, so you need a messenger to propagate the signal. So the second type of primordial non-Gaussianity that people probe, which is actually one of the best, easiest to probe, because it's such a striking feature, if you measure 2-point correlation function modulated by a very long wavelength mode. So if you have a long, imagine you have a big wave, and then you measure 2-point correlation function patch where the wave has a peak, where the wave has a valley. The 2-point function should be modulated. So this is a very clean effect, clean to probe, but it requires special physics. It requires an extra very light field. You need to explain why you don't see this field directly imprinted here at late time, so you need to model build to explain that. But in any case, we probe this, and then the nomenclature is terrible, so this is called local. It's the most non-local thing you can imagine, but it's called local non-Gaussianity. The reason, okay, so of course cosmologists are not insane. The reason it's called local non-Gaussianity is because you can mimic this correlation function by doing a local nonlinear transformation in the density field at the hot Big Bang. So you forget about the earlier mechanism. You just say that what you see, what you say is that the density field, the curvature perturbation, is a sampling of some Gaussian random field, and you write some Taylor expansion. Okay. So if you write this at reheating, then you can tell some story where this comes from, etc. Then this looks rather local because it says zeta of x is phi Gaussian of x squared. You give rise to the same signal. But if you want to explain during inflation, you're trying to correlate long modes and short modes, you need a very light message. So when you open any paper on inflation, people say local non-Gaussianity is a probe of multi-field inflation. What they really mean is that there's an extra light species. Okay? But now there's everything in between. Say again? No, the graviton is spin 2, right? So there's no, here there's no. At 4 points, there is actually, Filippo computed it, heroic computation for graviton. It's a very inspiring paper. It's quite a tour de force computation, this with the graviton. And somehow the benchmark is, can we make it as simple as possible, this computation with new methods? The problem is that the graviton, even though it's massless, it couples derivatively. So it doesn't really, it leaves some sort of long-range imprint. But then, of course, the second problem with the graviton is that we know the coupling, we can fiddle with this G Newton, so everything is very suppressed. I'll say something about gravity, a bit more about gravity in a second. If you, actually, I can say it now. If you stick the graviton in there, you would think that there is nothing, but there is one left over, which is the Newtonian potential, which is the longitudinal mode, the graviton. But then there's no long-range correlation, right? If you take the Newtonian potential, like the helicity zero part of the graviton, and you stick it in here, then you predict the type of non-Gaussianity you should get is actually of the equilateral type. And this is what Maldacena computed. I promise no reference, so I'm not going to write Maldacena, but Maldacena computed it in 2002. And here you make a prediction that FNL is order, and this requires some is order ns minus 1, but there's quite some confusion in the literature. It's FNL equilateral, just from this picture. You would think it's anyway. Let me not create confusion and explain it. So this is the actual signal. Okay. So it's FNL equilateral of order ns minus 1. So ns minus 1 is order 10 to the minus 2. So I can quote, before we go for lunch, I can quote some number. Let me define what FNL is. Just the strength of the 3-point function. Roughly speaking, is like this. So to soak up almost scale invariance, you take your favorite 3-point function, then you write it 1 over k1, k2, k3 squared. This k to the 6 is from scaling symmetry. Because of translation symmetry, the momenta need to form a triangle. There's k1, k2, k3. Then there is some shape function that depends on the details of which process you have in mind, self-interaction, messenger, etc. This only depends on ratios, right? K to and let's say that when you evaluate this, it's equal to 1 for K1. Okay. We define the shape function so that when the momenta are equal, the shape function evaluates to 1. And then again, bizarre historical accidents. You do the wrong thing, which is you put AS squared here, which is really a kind of a dumb thing to do. Because AS is the 2-point function, so this is the 4-point function of zeta. So you're comparing the size of the 3-point function to the size of the square of the 2-point function. You should be doing to the 3/2. Then you'd get reasonable numbers. So you're going to get big constraints on the overall coefficient. The overall coefficient is what we call FNL. But then you say, wow, cosmologists suck at measuring this FNL because the bound on FNL is like 50 or 100. But it's because you paid an extra factor of 10,000 here. So it's very Gaussian, very Gaussian. It should be to the 3/2. Anyway, I don't make up the rules. So that's the. So what are the current bounds on that? Of course, this depends now on which shape function you put in here. That's what I was saying, that you need some templates from motivated from theories. So if you put the equilateral template. By the way, one more thing about the bad naming. It turns out that in the pion Lagrangian, there is another equilateral-like vertex that has a shape that is in between this equilateral shape and the local shape. But it's an equilateral, non-Gaussian, it's just equilateral too. But because it was found later, and it's between equilateral and local, it's called orthogonal. So there are two vertices you can write down. One looks like roughly this pion pi dot cubed, and the other looks like pi dot d plus 1. So you got equilateral plus orthogonal. And just to finish, FNL equilateral is consistent with 0, and the current bound is order 50, mostly from Planck. And FNL local, this we can do better. The current bound, I don't remember, I don't think I have the number here, but it's order 5. This is going to improve. Okay? So galaxies are very good at, in principle, measuring this FNL local. So in fact, last year in California, this experiment called SphereX flew. It's a galaxy survey made to measure this, and it will improve on this number. If you're a pessimist, by maybe a factor of 2. If you're an optimist, maybe by a factor of 10. So we're gonna see some news about this number in a 2 to 3 year time scale. I think that's Planck. Then there are many things, and this one is exciting. This SphereX.
What does it observe? It observes galaxy distribution.
Yeah, so it observes the galaxy distribution, and then there's a specific biasing term, which is you should see more galaxies than you would have expected at large scales. You should measure some exponent of how much the amount of galaxies you see grows with scales compared to naive expectation. And this growth is connected. It looks like some violation of the equivalence principle because of this coupling. Because you couple very long modes to very short modes. And this violation of naive violation of equivalence principle is controlled by this FNL local.
Can you actually measure fluctuations here, or it's just the bounce?
Say again, fluctuations of what?
The dependence.
The actual distribution, like the actual correlation of the function of B.
Well, what we do is right. So as of today, I know there are people working on this as we speak, but as of today, we don't have a 3-point function of the data. What we do is we have a theoretically motivated templates. Then we go and contrast against the data and try to put a bound on it. So that's what we do. So it's template driven. Now at 3 points, the problem is that there are zillions of triangles in the CMB, so it's difficult to, and which ones should you keep around, which ones should you mask? But yeah, so I know that people are working on this now, trying to measure the 3-point function of the data. At 4 points, even the most general pipeline doesn't exist today. It's very hard to, but it's motivated to look for things at 4. The pipeline for analyzing these things is well developed at 3 points, and already at 4 points there are all sorts of challenges. Okay, I think maybe we can go for lunch, and then when we're back, we'll continue characterizing these non-Gaussianities, non-general messengers. Okay.
Yeah, no questions. No.
Maybe a quick one just to check the numbers. So you're saying that this normalization is a bit fine. In fact, it would be better if it was 3/2, and then
these FNLs would be very small, right?
so if I did 3/2, I would expect FNL to be order 1 number. Generically. I mean, it doesn't need to be that.
Let's say if the 3-point coupling was order 1, the theory is getting strongly coupled, you should see FNL order 100,000.
Yeah, okay, this is what I want to see.
So the theory is the fluctuations are very weakly coupled because the typical strength of here you probe products of coupling constants, right? But here the cubic coupling constant is of order this divided by 100,000. So small.
We measure it quite well. So we constrain these things quite well. In fact, I mean,
Yes.
Yes.
And the problem with this one is that with large scale structure is a big challenge to improve upon because the signal is peaked around equilateral triangles, but same scales start undergoing gravitational evolution, and the late time map is quite non-Gaussian. It's difficult to tell what's just from Gaussian evolution and gravity mixing things up and what's really primordial. There's a whole debate about whether you can detect this or not, and the jury is still out whether you can improve upon this using galaxies. In terms of naive number of pixels, there should be an improvement from galaxies, but it's difficult. This is cleaner because you correlate long scales with short scales. This is some sort of effect that is very difficult to mimic even with late time evolution.
The shape function, you just mentioned that. I mean, you need some.
Yeah, so somehow the business is how to compute this.
I thought you need to fix the fixed function to measure the
No, you compute some shape function, then you call FNL the thing that multiplies the shape function. Say you compute some shape function, and the answer is typically what you get is I don't know. I'm making something up. It needs to be dimensionless. So let me put it here. Okay. Say you compute some shape function, and it's this. So now what you need to do is you need to put, so when I put 1 plus 1 plus 1 here, I need to put 3 cubed here. So now this has, in the equilateral configuration, it evaluates to 1. But then I have a model where this was computed with some coupling constants up front. So all that stuff that appears, coupling constant squared, strong coupling scale, all that fun stuff, we call FNM. I will put a constraint on this number. But I haven't taught you anything about how to compute this. Somehow the business, the difficulty, the challenges in how to compute these shape functions.
So when we have those FNL bounds, those are from.
They are for very specific shape functions that have been computed for this type of interaction or for massless messenger. But then if you have all sorts of new physics, there are new shape functions that you should compute and you should put bounds on them, etc. Any more questions?
I don't know if this is I'm just trying to get a feel for these objects. So a peak in the, so I guess I'm thinking of like really measuring the 3-point function, but like a peak in this local non-Gaussianity function, the equilateral one, would somehow probe like a decay, like a lifetime of the messenger or something like that?
Well, it would be controlled by the mixing, right? So here there's some linear mixing of the messenger with the curvature perturbation. There's also this coupling constant. So it probes essentially this product. I could have a UV model in which these two vertices are controlled by the same scale, right? That's model building.
So okay, see you at 15 past 2.
Okay, thank you.
For those of you who want to come at the campus.